So the formulation for the final model in gradient boosting is basically h0 of x plus summation over gamma m, or you could call it as gamma I. Okay, let me change this terminology here slightly. So f capital M of x, right? Capital M of x is equal to small m equals to 1 to capital M gamma m into hm of x. This is what we saw, right, in the previous video. Now, one thing you'll notice is as m increases, what is capital M? M is basically the number of base models, right? We also used k for this earlier. Earlier in the videos, we said k is the number of base models, but I'm using m here because we saw on Wikipedia that they use m. So let any number, basically as the number of base models, whatever variable we use, as the number of base models increase, right, what happens? Your chances of overfitting also increase, right? While it reduces bias, that I agree, right? While it reduces bias, but you could also overfit, which means your variance also could start to increase, right? So what happens is as m increases, or number of base models increase, right? Of course, your bias is certainly reducing as we saw, but your variance also could increase. So this is how you do a bias variance trade-off. In gradient boosted decision trees. But there is one more nice idea called shrinkage that is often used in the case of gradient boosted decision trees, or in general gradient boosting. In the case of gradient boosting, there is a concept called shrinkage, which is very ingenious. So let's go to Wikipedia quickly and understand shrinkage, right? As it said, of course, we can find that optimal number. We can find this optimal m here. Coming back here before we go to shrinkage, how do we find the optimal number of base models? We find it using cross-validation, our standard tool, right? Because number of base models is a hyperparameter, right? Because as it changes, my bias variance trade-off will change, right? It's a hyperparameter that I can evaluate using cross-validation dataset. In addition to it, there's a very nice hack called shrinkage. Very, very nice idea in gradient boosting, right? Shrinkage works like this. What is your typical model? Earlier we saw that your FM, your model at stage M, is basically model at stage m minus 1 that you have at the end of stage m minus 1 plus gamma m hm of x, right? This is the model that we had at the end of stage m minus 1. This is the model we trained at stage m, and this is the coefficient that we got. And this is the final model that I have at the end of m stages, right? Now, shrinkage is a very nice idea. What it does is, to this formulation, it simply multiplies this whole thing with a variable v, right? I'm very bad with Greek alphabets. I keep getting confused. That's why I'm just calling it v here, right? V is called the learning rate. And remember, v lies between 0 and 1, right? Typically people take v to be roughly equal to 0.1. Of course, v is also hyperparameter here. Now let's see what happens. If v is small, what happens? Let's start this. V is also hyperparameter. Let's not forget that, right? This is called the shrinkage value. V is called the shrinkage, right? V is also a hyperparameter. And how do we determine hyperparameters? We determine them using cross-validation dataset. But intuitively, if you think about it, if V is very small, let's say V is 0.0001, very small. The only requirement is that your V should be greater than 0 and less than equal to 1. Right? If it is exactly equal to 1, you have the old formulation, right? If it is small, what are we saying? We are saying that we are giving, in addition to whatever weightage we found using gradient boosting, we are going to reduce that weight, right? That's what we are doing, right? This is the model that I have. I found this gamma m by solving a small optimization problem earlier, right? Now what I'm saying I will reduce this gamma m by a constant v. Isn't it? Now that v, if it is very small, what I'm saying literally is that I'm going to give less weightage to this model. So what happens is as v reduces, your chances of overfitting reduce, or in other words, your variance also reduces, right? If v is large, of course, v can at most be 1, right? As v increases, your chances of overfitting or variance also increase. So you have two hyperparameters at the end of the day. You have M, which is the total number of base models, right? And you have V, which is the shrinkage coefficient, right? Based on, of course, the ideal thing would be to actually do cross-validation. The ideal thing will be to do cross-validation with something like grid search or random search on both these variables. You have M, which is the number of base models, and you have your V, which is your shrinkage. You do a grid search on both of them and find the best ones. Whichever values of M and V reduce your cross-validation error to the minimal, right? That's the ideal way to do it. But both M and V can be used to control your bias variance trade-off, to control overfitting, whether you're overfitting or not. Because remember, in GBDT, it's very, very common. One of the most common things I see is when you apply gradient boosting or specifically gradient boosted decision trees, people often overfit. Because it's very, very easy to overfit, right? Because if your M is large, if your M is very large, it's going to be trivial to overfit the data to your training set, right? Overfit the model to your training set. It's going to be extremely easy. So be very, very cautious when you train a model. Always use your cross-validation data, and please do a grid search on both V and M so that you find the best values of M and V without overfitting. Otherwise, it's going to be very, very commonplace. I've seen a lot of cases where people would train a GBDT and trivially overfit it. They would take M equals to a very large value and they would trivially overfit it, right? So be careful. Always in any model, not just in gradient boosting, always use cross-validation to get your hyperparameters right. Here we have two hyperparameters, the shrinkage and the number of base models. So that's how you control the urge to overfit. It's very, very common. Let me tell you again. I've seen this multiple times, especially by people who are getting started in machine learning. So be careful. Please don't overfit GBDTs. If you overfit GBDTs, all their power is gone. So you have to be very, very cautious not to do it.